Welcome to the introduction to tree data structure. A tree, also known as a prefix tree, is a specialized tree-based data structure that is used for storing and retrieving strings efficiently. Let's dive in to understand more. A tree, pronounced trie or tree, is a tree-like data structure where each node stores the letters of an alphabet. Tries are also called prefix trees as they organize data based on prefixes. You might also hear it being called a retrieval tree. This data structure is efficient for prefix-based operations such as autocomplete and spell checking. Let's explore the structure and properties of a tree. The root node represents an empty string. Each node in the tree stores a character and has branches or edges that connect it to its child nodes. Every path from the root to a node forms a prefix of a word stored in the tree. Paths to specifically marked nodes represent complete words. Words that share common prefixes also share nodes in the tree, which makes tries memory efficient when storing similar strings. Let's examine the structure of a tree node using a Python implementation. Each tree node contains a dictionary called children. This dictionary stores child nodes, using characters as keys. A Boolean flag is end of word, marks the end of a valid word. Here's how to insert a word into a tree. Starting from the root node, iterate through each character in the word. For each character, check if a corresponding child node exists. If a child node doesn't exist, create a new node. Move to the child node. Finally, mark the last node as the end of the word. Let's consider an example. We want to insert the word car. First, we start with the root node. Then insert character C. After that, A and finally R. Mark R as the end of the word. Let's see how to search for a word in a tree. Begin at the root node and traverse the tree, following the path of characters in the word. If a character is not found in a node's children, the word does not exist in the tree and we return false. If the entire word is found, check if the last node is marked as the end of the word. If it is, then the search returns true, confirming the word's presence. For example, we search for the word car. The search will return true. Now let's look at how to check for a prefix in a tree. Begin at the root node, then traverse the tree for each character in the prefix. If any character is not found along the path, return false, indicating the prefix does not exist. If the entire prefix is found, it returns true, confirming the prefix is valid. The tree can also be used to list suggestions to the user. Example: searching for CA will return suggestions like CR, card, cat. Let's discuss the time and space complexity of a tree. The time complexity for insertion and searching in a tree is of the order of m, where m is the length of the word. This is because, in the worst case, you need to traverse all the characters of the word. The space complexity of a tree is of the order of n times m, where n is the number of words and m is the average word length. This is because each character of each word is stored in the tree. Time complexity is independent of dictionary size, making tries especially efficient for large data sets. Tries trade space for speed. They use more memory than other data structures, but provide faster lookup times. Hash tables offer order of 1 lookup time, but cannot efficiently find prefixes. Balanced binary search trees offer order of log n, but also lack prefix capabilities. Let's see the real-world applications of tries. Autocomplete predicts and suggests words as users type, using a tree to efficiently find all words with the given prefix. Examples are search engines, mobile keyboards, IDE code completion. Spell checking quickly verifies if a word exists in the dictionary and can be extended to suggest corrections for misspelled words. Examples: word processors, browsers, email clients. IP routing uses specialized tries to store routing information and perform longest prefix matching for IP addresses. Examples: network routers, routing tables, packet forwarding. Bioinformatics stores and searches DNA or RNA sequences to efficiently find patterns in genomic data and enable fast substring matching. Examples: genome sequencing, pattern matching in biological sequences. In summary, tries are specialized tree structures optimized for efficient string operations and prefix searches. The time complexity for operations is of the order of m, regardless of dictionary size, where m is the word length. They are excellent for applications requiring prefix matching, auto-completion, and dictionary lookups. Tries involve a space-time trade-off, using more memory but providing significantly faster string operations. They offer simple implementation with powerful capabilities for string-related problems. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.